Hello everyone. I hope all of you are healthy and safe. I'm Akshay Pamar. I'm the Vice Chair of TAIym. And on behalf of TAIym, I welcome you all to the 12th webinar of our webinar series. Today we are privileged to have collaborated with Rajat Gangrade. There is a lot to talk about Rajat. He has achieved quite a lot in his young career. Right now, he is a PhD candidate in underground construction and tunneling department at Colorado School of Mines. His doctoral research focuses on quantifying, understanding, and communicating spatial uncertainty and risk for soft ground tunneling application, which is a very contemporary topic to have. Prior to joining his PhD at Mines, he has worked in the industry for about 4 years, couple of years at Jacobs in Iowa, and another couple of years with AECOM on Mumbai Metro. He also has a master's in geotechnical engineering from Virginia Tech, and his basic graduation is in civil engineering. So coming back to the today's topic, today he will talk about AI application in risk assessment of soft ground tunnel projects. I mean, this is a topic which has been in discussion with the TIYM in and around the discussions we have. So it's something we all look forward to, and it's good that he had some experience to share on this with all of us. As always, I request all of you to keep your microphones and video off so that it doesn't interrupt the flow of the presentation. And we will take the questions in the end as always. So when he finishes with this presentation, you can select the raise your hand option from the menu bar, and then we will take your questions one by one. In the end, we will have our chair Sandeep to address you as well. So without much ado, I thank Rajat again for accepting our request and invite him to start the session. So over to you, Rajat.
Thanks, Akshay. Thanks, Akshay, for the introduction, and thanks to TAIym for reaching out and organizing this. I'm quite excited to talk about something that is going to take over our industry and our academia. When I say our, I mean people who are involved in civil engineering, mining engineering, rock mechanics, soil tunneling, hard rock tunneling, AI or artificial intelligence or machine learning is going to take over the industry and the academia by a storm. That is going to happen, that is bound to happen, because everyone wants to learn from data. And you must have seen the data war out in the digital market right now. What you observe with Geo or Facebook or WhatsApp and Instagram, people want your data, and people want to know what are your preferences, so that they can give you suggestions. If it's a Friday evening, you will start getting suggestions of the best tandoori chicken you can get near your house, or the best pizza place, and their offers on Wednesdays and Tuesdays. So stuff like that. And our world is no different. Our construction world is no different. Everyone wants to finish the project as soon as possible in the shortest amount of time, with minimum expenses, with minimum risk. And for that, we need to understand how the world operates, or how our construction industry operates. We use machine learning and artificial intelligence in our day-to-day life. And these words, before we knew them, that, oh, this is called artificial intelligence, we have been using it for past 150 years or 200 years or 500 years, or rather at the start, since the mankind started to look at inventing things. So we have been using it subconsciously, and that's one of the biggest advantages of talking about this, because it is intuitive. I find it very intuitive. And the way I would want you to think about artificial intelligence before I start this presentation is think about the ads that you get on your phones, or the ads that you get on Facebook or the ads that you get on Instagram. Think about it that way. They're helping you out to make your life easier, but they're also taking away the data. So that's pretty that's the part and parcel of the game that you're dealing with. But the objective is you make the life easier for someone who's who's a customer or who's a product or who's a tool. So in that case, artificial intelligence is applicable and in our construction industry. And the biggest motivation I feel, the most exciting part and the motivating part for this application in our industry is what we can learn from other fields. How has artificial intelligence applied in medical science or medical research, biomedical engineering, mechanical engineering? That's all. That's the motivation and that's the inspiration that tunneling community can adapt to. And I have always found, and my research group over here has always found excellent examples outside of civil engineering where we can come back and start looking at how we can apply those concepts to our projects and to our community. So in this presentation, I'm not going to discuss anything about what machine learning models to use, what's the criteria to find which are the best predictor variables, how do I identify whether I should, if my model is correct or not, none of that overly technical stuff. I'm going to give a very holistic view on what artificial intelligence application in tunneling projects looks like. And there is much more, but I'm just going to walk through a few examples. So as I said, underground construction and everything around you is rapidly going digital. When you are working on any civil engineering project or any geotechnical engineering project or tunneling project, you would want to see the progress of the project. You would want to have the data on your fingertips so that you can just drag and scroll and zoom and figure out color code and figure out what is the engineering behavior of the construction. And that's the key, because you do not have time and you do not have the intuitive strength to look at 1,000-page PDF or a 5,000-page document that comes in as TBM construction reports or baseline reports or interpretative reports. You do not have time to do that. And more than the time, I think it's about, are you going to find real value by observing things manually? Or are you going to find real value by observing things digitally? So that's where I think as a community we need to understand and grow that digital is the future, and these sort of platforms where you can visualize and see where your tunnel project is heading towards, where your TBM is, what sort of locations you're crossing. Where are your instrumentation and monitoring sensors? If you select a sensor, then what sort of ground deformations you are getting? This is important. This is extremely important. And there are a bunch of companies that do it. I'm pretty confident the people on this call have heard about almost all of these. But the objective is, if you have more data, the better is going to be your assessment of how the ground is going to behave, how your machine is going to behave, and then whatever models you develop for risk assessment, how are they going to behave? And then there are multiple things to look at. I mean, we get Excel sheets of data in terms of TBM operations, we get boreholes, we get ground deformation data, we get TBM operation data. I think when a TBM operates, about 100 to 150 sensors are recorded. So you can imagine, and they are recorded every 10 seconds or 5 seconds or 15 seconds. So you can imagine the amount of data that's coming towards you, so that you can, probably the objective is to use that data to understand how our tunneling is coming along and develop better models. So when I say better models, I mean you eventually want a tunnel model that captures the ground, the machine, the behavior of excavation, and then what environment you're building in. So it's quite important. It's quite important to understand first basic need for any artificial intelligence or machine learning application is that you need to have data. So currently in practice, as I was talking about, there are stacks of PDFs, static PDFs. You're looking at 1,000 pages of boreholes. Pages of boreholes are not going to help us out. I mean, as an engineer, I have worked on Mumbai Metro. It's a 21-mile underground metro corridor. You will be tired looking at PDFs of boreholes to identify, to understand what sort of geology I'm looking at. So at that point of time, I didn't know this, but now I think visualization of the data is extremely important. And I'm trying to play this video. Okay, yeah. So this is the sort of visualization that you would want to see on a tunnel project, where you can see the tunnels, and then you can see the boreholes. The boreholes are color coded according to the geological formations or the geological units. But that is what I'm talking about. Even if you have data, you need to understand how we can enhance the interpretation of the data. Sure, if you turn up one day with 6,000 pages of PDFs, it's not going to help. You need to develop better visualization techniques so that we can harness all this information into our machine learning models. So that's the key, because the two key components we are going to discuss about in this presentation is, and I always love talking about these two components. One is the TBM, be it a slurry machine or be it earth pressure balance machine, or even if it's not a TBM, even if you're doing an NATM or an SEM cavern, the type of excavation. So one is the machinery, and the second is the component that holds the biggest risk on any tunnel project, and that's the ground. So we're going to discuss these two aspects pretty much detail over here. So this is what we want. So you can see a bore log over here. We have different soil types. You have SPT values. You have Atterberg limits test. You have fines content. How are you going to relay all this information to someone for the complete length of the tunnel alignment? And with more and more urban projects coming up and the construction control or tolerance that we have, we need to minimize the risk and the damage to the community as much as possible. And my understanding of why we need to minimize the damage to the community is because it will build their confidence into adapting tunneling as a viable solution for infrastructure development. Otherwise, people will be more involved into building flyovers or bridges, and then the aspect that helps in urban planning is just not going to flourish. So in this case, we want these sort of visualizations where we can relay this information, understand, and develop our models accordingly. So that's one of the key foundations for any machine learning or AI applications. And then understanding, how your data distribution is. So as a great example, in Mumbai Metro, the strength of the rock or the strength of the soil, they are not uniform throughout. It's not that you get the same strength or UCS from Cuff Parade to Seeps. I mean, it changes and stuff changes. So you need to understand statistically what is the distribution of your data. And once you understand that, you're trying to understand the ground. And once you understand the ground, you will be in a very good situation, or an ideal situation, I would say, to develop and apply those machine learning models. So as I said, have the data, understand the ground, do investigations on how the parameters are changing, and then think about what type of risk you want to model or what type of assessment you want to do, and then think about developing those models. So though I think these are the steps that I'm trying to relay out over here on how to approach ML and AI stuff in construction. And understanding the ground is important. I mean, That's where I'm coming at and focusing upon again and again. And right now we'll be talking about a little briefly about the uncertainty in the ground and what I mean by understanding the ground. So in this example over here, you see there is a layer of sand over clay. And this is, let's say, a PDF of a geological profile that you have from the GIR that your consultant has developed for you. So you're a tunnel contractor on the project. When you look at this, you are like, oh, all right, I'm going to just tunnel in clay. Fine, fair enough. It's over consolidated fat clay. I'll be very happy to tunnel in this and we can finish the project in 3 months. That's fine. I mean, yeah, we can do it. So you'll bid accordingly. You will bid. You will have your construction means and methods. You will have your budgeting. You will have your pricing. You will have your timeline, all based on a single profile that your consultant has developed for you. Obviously, the consultant states the limitations at the end of the report, but that's not the point of discussion over here. The point of discussion is how do we understand and how do we take decisions in uncertainty? You know what would happen in reality? In reality, this would be the case where with 75% confidence, there is a probability that your sand layer actually extends up to the face of the TBM. Now, many people would be thinking, what difference is it going to make? Well, if you have cohesionless soil at the top in the tunnel crown and cohesive soil at the bottom, it's going to make a huge difference on how you operate the tunnel boring machine. Your pressures are going to shoot up. You're going to have a lot of water inflow because of higher permeability of sand. And you might even frag the ground and cause heaving or settlement at the surface. So there is uncertainty in the ground, obviously, and you need more data to understand what sort of uncertainty you're dealing with. You need to have a probabilistic assessment of the ground conditions. Never rely on deterministic ground profiles, what I'm showing you on the screen. They are most often not true. What is required is an assessment of this sort, where you kind of take into consideration all the possible scenarios and then go ahead and plan your construction or develop a machine learning model, develop a risk assessment model. It all depends on that. So as I said, there's more intelligence and more automation coming up. And for that, everyone wants data. So you can see over here, the self-driving cars. The way they have understood how these cars work is purely based on image identification. I'll show that in the next slide. But yeah, also on probably understanding what sort of road conditions are there. So they're trying to gauge and gain as much as data possible. And you know what they actually did? They actually drove. Well, that's a poor statement, but they had a driverless truck going for 132 miles over here in Colorado, and it was a beer truck, and just fabulous. I mean, drove in a single lane without disturbing the rest of the traffic, identified the vehicles that were ahead of the truck, maintained the speed. So these sort of adjustments can be made, and tunnel boring machines are nothing different from a vehicle. It's like driving a car. You need to understand what your conditions are. You need to understand what speed I want to go with. You need to understand how much I want to push. And all this is possible if you understand the ground, if you have more data, more geotechnical information. And this is how this is how the Uber that was driverless actually works. So when the car is driving, it is constantly looking on the road and seeing, oh, there's a person, there's a traffic light, and there are people over here. Oh, this person might just cross the road. So it all depends on having as much as data possible. What this is doing is giving you the freedom or giving you enough guidance and freedom to take informed decisions. That is the concept we are going to live with. And one of the best examples that I think of artificial intelligence is just imagine this. You are driving from your home to your office, all right? And there are multiple routes that you can take. of course. And you need to identify based on the traffic, based on the time of the day, based on how quickly you want to get to office, based on the maximum speed you want your car to drive. So based on all these factors, you can come up with an optimized route and choose a route. Just a fascinating example. And if you add to this, if I am the provider of a driverless car, I would sell the rights of driving the car on a particular route so that the customer in the car looks at the advertisements on the board that are on the hoardings. So as much data as you have, a person like me will be able to develop a more reliable model for the consumer, and in this case, the consumer is our tunneling community. So I have stretched this example of vehicle traffic. Imagine you have a network of tunnels in a city, and the best example is either Singapore or New York. So you have tons of tunnels done in the city, and then now you want to dig a new tunnel. What are you going to rely on? Your geology is almost the same. It's not changing quite drastically. And you have all the TBM information, all the boreholes that have been drilled in the past 10 years, all the TBM information from past 10 projects over the past 10 years. You have everything. What is your objective? Your objective will be to find a way to finish the construction of the new tunnel as soon as we can, with minimum risk and with maximum speed, of course, and set a record, right? And that's the objective of the AI framework. So harness the data as much as we can from all the projects and use it for future projects. But yeah, your question might be right. Hey, Rajat, the geology over here and the geology over there is completely different. How can we apply these models? Definitely, that's a great question, pretty intuitive. But if you have a robust model developed, and when I say robust, the meaning of robust here is it is applicable to different scenarios and different situations. So if you have that developed, then probably you can apply it to different projects with different geotechnical conditions, with different TBM types. All you need to do as an engineer is understand what's important, what's not important, and decide on the variables, or decide on the machine learning aspects, or decide on the raw information that you have. So taking an example of New York subway over here, it's pretty dense network. And you have tons of tunnels going from one corner of the city to another, going through different geological units, dug using different type of TBMs, huge amount of data set available out there in the market. But the point is, can we use all this? Even if it gets to you, how are you going to use all this? And I believe artificial intelligence can help us with that. You want to select what will be your best TBM. You want to select what would be your best options for installation of liner, whether a slurry TBM will do or EPB will do, and stuff like how fast I can go, what would be the maximum thrust force, will I be disturbing the community? So it's all related. It's all related, and that's why I think the key point over here that we want to take away from today is accelerating the projects. If there is one thing that you can take away from this presentation, take this. Artificial intelligence is for accelerating the construction of the projects and nothing else. The rest of the things, reducing cost, reducing claims, optimizing project aspects, sure, they come as a byproduct. But your biggest objective and aim is acceleration. You want to go as fast as you can. That's the fundamental approach. So today we are going to talk about four kind of cases or use cases, I want to say, of AI. One is understanding the as encountered ground conditions. The second is, can we do advanced rate modeling and forecast the advance rate? Before I touch upon 3 and 4, I want to talk a little bit about the second point over here. Immense amount of work is done for advanced rate modeling in hard rock tunneling projects, and very less is done for soft ground tunneling projects. So if you just Google Scholar or if you just Google advanced rate modeling, the first 100 papers that are going to get is all will be on hard rock. And that is purely because hard rock tunneling had its birth from mining, and it's one of the oldest construction methodologies in the world, where communities have excavated the rock and built infrastructure. So there has been huge amount of investigations into hard rock, but hardly anything as small as a peanut in case of soft ground. So my focus with this presentation is going to be to talk about soft ground conditions. And as I said, I'm not here to discuss type of algorithms or type of models. I'm only here to show you what sort of other possibilities. So as encountered ground conditions, advanced rate modeling, cutter tool wear forecast, and then ground deformation modeling will be something that we'll walk through, and we'll see how what sort of information do we need and what sort of results can be seen from this. So yeah, I mean, why do we need as encountered ground conditions in the first place? That's a very key question to understand. Say you're doing closed phase tunneling, and if you're doing closed phase tunneling, you really do not see the ground. And whatever you see on the conveyor belt is something that is excavated maybe 5 or 10 rings earlier. And then when the liner is installed, that material is actually coming out a bit late. So it's not easy to understand what sort of ground you have encountered, what sort of conditions your TBM has encountered. And when you look at aspects such as thrust forces or advance rate or torque or cutting wheel rotation speed or the penetration, each single TBM operating parameter is related to the ground. So in order to apply or understand what sort of assessments need to be made, you need to understand first the as encountered ground conditions. And sometimes in cases of where there are differing site condition claims, the contractor wants to understand, hey, as compared to the geological profile in the GIR, what was I excavating? Was it clay or was it sand? So you want to look at the TBM operating parameters to understand what sort of ground it was. And always remember this, your tunnel boring machine is the only thing that goes into the ground. So your tunnel boring machine is the only thing can tell you what the ground type is. Your borehole scan with a very subjective assessment, your engineer with a very subjective assessment. But if you look at the actual data from the machine, only then you can identify what the ground is. And that's what the aspect here was. And this was some of the work that was done before I started my PhD. And while I was here initially, I wasn't involved in any of this work. I was mainly involved in cutter tool wear and ground deformation. So I would give the right credit to the right people over here. And there's a PhD student who just graduated with under Professor Muni. His name is Hongji Yu. He's from China, and he does excellent machine learning algorithms for identifying what sort of ground was encountered and more on AR modeling. But yeah, that's the objective. So this is geological profile from a project in Seattle. Very complex glacial geology, immediate transitions between cohesive and cohesionless material, very critical. Risk, there's immense amount of risk on this project. And our research group applied machine learning to understand what was the actual ground type that was excavated by the TBM. And this is some of the example results that have come out from the study. So you can see the top one, the top figure is the geological profile from the GIR, or what we call the GBR over here in the US. And that is interpreted by an engineer, experienced engineer, from the borehole data. And over here at the bottom, you can see applying machine learning to TBM parameters. So we are looking at the aspects that get influenced because of the ground, which are the torque, thrust, cutter head rotation speed, what type of soil conditioning they used, why they used it, what were the articulation forces, whether the TBM was dangling a bit upwards or going downwards. There are sensors for everything. As I said, about 500, as I said, about 100 to 150 sensors are recorded every 5 seconds, 10 seconds. So you can imagine the size of the data set. So the top one and the bottom one, and in this case, you can see some of the predictions from the machine learning model that show that brown material was present over here within the tunnel envelope. But over here in the geological profile, you really do not see that. But whatever was observed from the TBM data, it showed a high presence of the brown material for at least for about 500 rings, and that's substantial. 500 rings is about 1,000 meters. If you consider 2 meters to be the length of the ring, longitudinal length, you're talking about a kilometer over here. So that's quite large. Over here, in case of this is a great example. So the blue material which you see is the cohesionless material, and the green one is the cohesive material. And as I said, there is a significant amount of risk when a TBM goes from one to another of the cohesive or cohesionless. But the TBM operating data shows that this cohesive material extends to a much larger distance from what was shown in the subjective geological profile. And this sort of information is eventually used for understanding what TBM excavated. And then, the contractor, as I said, the contractor uses it sometimes to understand how my machine operated in different sort of ground conditions. So that's one of the great examples of what machine learning can do for you. And, if you have enough data, what you can identify about the ground from machine learning aspect. So along with that, as this was within the tunnel envelope, then we identify what was the percentage of each soil type. And the soil types are mentioned over here. What was the percentage of each soil type within tunnel envelope compared to the subjective geological profiles? And you can see it's a pretty decent match. It's a pretty close match to what was anticipated, and then what was actually shown by the TBM. The highest fluctuation was for the cohesionless silt and fine sand, and for the cohesive clay and silt. Otherwise, the rest of the two soil types, they were pretty much predicted almost correctly by the AI algorithm or the ML algorithm. So yeah, that's a type of application that we are looking into. Another aspect, I mean, what the as encountered ground conditions, and I should have put this slide earlier, but I talked about this briefly. It's using the borehole data, it's using the TBM data, and then it's combining both to understand, what is the as encountered ground. So if you see higher torque and higher thrust, then maybe you are going through a higher strength ground, which can be either a till deposit or a cohesionless sand and gravel. And this is just an example I can give you because I've looked at this data closely. But that is how the intuitive thinking works when it comes to machine learning models. There has been success, and yeah, I mean, for the entire project, we could paint a picture on what sort of soil types were encountered as the TBM excavated, and as per the AI model. And as I said, there was close resemblance to the one in the GBR or the GIR. So the biggest problem with developing these models or any model in construction industry is someone is going to just stand up and ask you, how are you going to validate this? How can you say that your model is correct? So in this case, we check the validity of the model with the geological profile provided by the engineer. And in that case, since it was a pretty good match, we could say that whatever the TBM excavated and painted a picture about the actual ground conditions, and that can be used for further assessment. So again, the same example that I showed earlier. The other was the advanced rate modeling. That is something that we do as a research group a whole lot, where say you have excavated 1,000 rings on your tunnel project, and you want to forecast what would be your advance rate given the ground conditions for the next 1,000 rings. And you can then apply machine learning algorithms to look at the variables that affect advance rate. So obviously, advance rate is affected by what is your chamber pressure? How fast are you excavating? Is your chamber pressure high? What is your torque? What is your screw conveyor rotation speed? If the screw conveyor rotation speed is high, that means your material is carried from the chamber to the conveyor belt at a much faster rate. That means you're going faster. That means your advance rate is higher. The other aspect is the penetration rate. If your penetration rate is high, that means you're biting a large size of the ground within shorter time. So you're going faster again. So these sort of variables that we look at help us understand what would be the advance rate of the machine. And it's not rocket science. I have this great story. Let me tell you this story. There was a computer science engineer over here in our university, and they were doing AR modeling, and he was interested in AR modeling. Remember, computer science, no domain knowledge of tunneling. Okay, so that guy just comes and says, "Give me the data set, and I'll figure out what to do with it. And I don't need you to tell me about domain knowledge and stuff." And we were like, "Fine, okay." And he takes the data set and he runs these complex algorithms for 3 months. And then he comes back and says, I found a one-to-one correlation between two variables that can influence between one variable and advance rate. And you will be surprised with the results. I'm getting an R square of 0.99. Obviously, an R square of 0.99 is your variables predicting the advance rate almost accurately, right, to the pinpoint. So he comes back and says the weight of the material on the conveyor belt is an influencing factor of your advance rate. And as tunnel engineers sitting in that room, the only thing we could do was laugh because we knew this. We don't need complex machine learning algorithm to tell us that. So what I'm trying to come up with is the most important aspect that you want is domain knowledge. If without domain knowledge, you're trying to apply machine learning algorithms, it's a very simple thing of the best phrase in numerical modeling, garbage in and garbage out. So that sort of understanding an engineer needs to have. So when I was talking about advanced rate modeling, you need to do good amount of research and understand what sort of TBM operating parameters are going to affect your advance rate. And these are some of the results that we have where we see a good fit. This is still not a great fit, but a good fit between what was measured and what was predicted by the model. So now, once you have validated, all right, my model performs well and model performs fine, you can then apply this model to future rings to estimate what your advance rate is. And once you have estimated your advance rate, you then can figure out how much time you're going to take for excavation and all the construction schedules part. So major takeaway is domain knowledge. If you do not have domain knowledge, if you just randomly pick a data set and you apply some random algorithm, you're not going to get results, and you're going to get results which are going to be very useless for you. So always keep that in mind. That's one of the keys on machine learning aspect. Moving on, I would then talk about one of the projects that I have been involved in, and we applied machine learning to this for cutter tool wear and ground deformation. Pretty interesting project. This is a northeast boundary tunnel project in Washington D.C. And it's an 8 kilometer long, 8 meter diameter tunnel. Um, just like any other urban project, the tunnel passes through open spaces and then moves into the congested urban environment. And there is an important Amtrak rail yard over here. Amtrak is used here for intercity rail transport. So you have a rail yard over here, and then you're into congested urban environment and urban setting. So that's how the project is laid out. What the contractor wanted us to do was do two things. One, estimate what the cutter tool wear will be, or forecast what the cutter tool wear will be. And second was forecasting how much of ground deformations I'm going to experience in the future. Sure, they could have run numerical models, but they wanted to have a stab at artificial intelligence and machine learning applications. And yeah, the whole objective of this was to see the capabilities of AI on a tunnel project in real time. I mean, on this project, we have been applying models, and we are communicating with the tunneling contractor on almost a weekly basis, giving them indications on where do you need to have your next tool change, where do you need to have your next intervention, how much of ground deformation you're going to experience, what phase pressures you should use. So you can see it's controlling the construction aspect to an extent where you're mitigating the risk out of the project. And that's the objective. That's what we have been working for. So with this introduction about this project, I want to give you a brief overview of how we are doing this. So we have the input data, we have the geology, we have all the ground monitoring INM data, and then we have all the TBM data. So as the TBM is excavating, we are getting all that information on our server. We are downloading that. As engineers, we are looking at the patterns, the trends, the plots, and then we are looking at what sort of geotechnical conditions are possible over there. We are not looking at a deterministic profile. We are looking at a probabilistic profile. And then we are developing these 3D models of ground. So generally in practice, in industry, what you see so far are 2D interpretations. But over here, I'm developing 3D models of the ground so that we take into consideration the geology within the project site in all the dimensions. And similarly, developing geotechnical parameter models, like what is the SPT, what is the plasticity index, what is the moisture content. And we are processing all that information along with the TBM and doing those and running those models on our servers and returning back that information to the contractor in a way which is easy for them to understand and make decisions. So always remember, your objective is to mitigate risk and have easy decision making for someone. So I think this is a great graphic because it shows the complexity of what we are doing, the complexity of having the ground, having the INM data, and then having the TBM data. I think and very importantly, INM data and TBM data are dynamic information. They are not static. So I think this is a phenomenal arrangement of data to just set up the machine learning applications for this project. So again, a brief introduction of the project. There were about 106 boreholes drilled for 8 kilometer project. You can see the overburden, the ground conditions. Pretty stratified geology, if you ask me. where G1 and G2, they are cohesive material, and G3 and G4 are cohesionless. And we'll come to this. Why am I talking about this? You'll get a feel for it in the subsequent slides. And then, as I said, doing geostatistical modeling, that's what my PhD is on developing ground models for tunneling applications and identifying tunneling risk. So as I said, the contractor was very concerned about tool wear and was very concerned about tunnel-induced building deformations. And we asked him, why is he so concerned about tool wear? And his response was, every single tool that you see in this graphic is worth about 3,000 US dollars. So that comes out to about 2 lakh rupees in India. And that is what your single tool on your cutter head is worth. So you can imagine if your cutter head has about 20 tools on it, you are talking about an investment of 40 lakhs. And you really do not want to be in a situation where you are not observing what the tool wear is, and you're not observing what where you want to change the tools, and you're also not observing subsequently how your tools are affecting your construction. A brief background: if your tools wear out a lot, your construction efficiency goes down because your machine is not then excavating at the same efficiency. And then obviously every tunnel engineer's favorite scenario of tunnel-induced building deformations. If you have not, you should go back and see Anshul's presentation from the MIT workshop last week. Fantastic on tunnel-induced building deformations. It was a worthwhile watching presentation for every engineer out in the industry. So yeah, we use AI over here to forecast this. So let's start with cutter tool wear. The biggest problem with cutter tool wear is you do not have a continuous measurement of tool wear. I mean, it's not that there is any sensor installed on the tool that you can then have a continuous assessment of how your tool is wearing out. It's only when you observe the tool at interventions, maybe at an interval of 500 or 1000 rings, then you realize, oh, all right, this is the tool wear. So we wanted to overcome that situation. We wanted to understand how our tool is wearing out continuously and how it is going to wear out given the ground conditions. So there are some empirical models, but the biggest problem with those are their TBM operation is not taken into consideration. So I always give this analogy where your tool is like your brake on your vehicle. The wearing out of the brake depends on how you drive the vehicle. If you're a rash driver and if you keep on pumping up the brake, then it's going to wear out much faster. The brake pads are going to wear out a whole lot faster. But if you're a very careful driver, where you're pressing the brake very gently, it's not going to wear out that quickly. There is going to be maintenance required, but not so severe. So it all depends on how you drive the machine, but that is not taken into consideration in some of the empirical models that forecast tool wear. But what AI can do is AI can help us understand this unknown relationship between the ground, the TBM operating parameters, and the tool wears. And that is what we'll focus upon. So this is what the contractor was interested in. What is the wear rate? How many number of tool changes? How can we optimize the locations of interventions? And this is all taking into account the ground variability and TBM operation. So when I say ground variability, I mean you're taking into consideration the uncertainty in the ground conditions. And then the limitations that come up with this empirical approach that I was talking before, where TBM operations are not considered. There is no guidance as such, which tools to replace at the next intervention. I think that's the key question for any contractor, or even for an owner, if the project is being planned in that sense. So we go through, develop realistic profiles of ground conditions. So one of the biggest aspects that affecting tool wear is the abrasivity of the soil. and using the soil geological profile, the D60 grain size distribution, the SPT values, we develop an abrasivity profile. And I would want you to see the first plot over here and the last plot over here. So as you're going from left to right, your ring numbers are increasing, and you are looking at G3 and G4 material as orange and maroon. Now correlate the same plot over here, you would see that G3 and G4 are the sections where there is higher abrasivity, which makes sense because G3 and G4 are cohesionless, dense sand with a higher grain size. So higher your grain size, the more your abrasivity will be from the empirical equations. So that is why I was stressing a little more upon the G1, G2, G3, G4 initially, because I wanted to show what soil types can translate to a higher uncertainty, a higher abrasivity in geotechnical conditions. And then you kind of understand, what is the uncertainty in your abrasivity. You kind of understand what your ground is. And this is the first step at the start of the presentation, what I was talking about, understanding the geotechnical conditions and the ground. And that's the key to set up any machine learning algorithm. So yeah, how do we model this? And we select, as I said, you need to have domain knowledge for this. You need to understand what sort of parameters are going to affect your tool wear. And in this case, we have penetration rate, cutter head torque, thrust, chamber pressure, what is the rotation speed, your liquid flow rate, foam flow rate. The higher the foam quantity or the higher the foam quantity that you provide, the lesser will be the wear of the tool because you have conditioned the soil to be soft enough for less wearing out. So you need to understand the dynamics of what is going on, how your machine is going to operate, and what sort of parameters you want to look at. Tool travel distance, it's common knowledge, sometimes non-intuitive to people who have not looked at it, but the tools at the periphery of the TBM wear out faster as compared to the tools that are at the closer to the center of the cutter head. And that's because the larger periphery gives them a larger travel distance. So with each excavation of ring, your tool is doing more work. Your tool at the periphery is doing more work as compared to the tool at the center, and that's why you get more wearing out at the periphery of the TBM. And then we look at intervention records. What was the tool wear at intervention 1? What was it at 2, at 3, at 4? And then we predict what is going to be the tool wear at future interventions. That's how this machine learning model is set up. And so yeah, we do model training from for about 2,600 rings, where we have data on 6 interventions. We have soil abrasivity profile. We integrate all these 3 sources of information to forecast what is your intervention, what is your tool wear going to be at the next immediate intervention. That's kind of key. That's interesting to understand how much your tool is going to wear out when you're at the next intervention. And we are looking at, I should have mentioned this before, but we are looking at 8 tools. It's not really necessary that you have to change all 8 of them when you're doing an intervention. As I said, the tools are very expensive. So you need to understand, do I need to change all of them, or do I just can live with changing 3 and not changing 5, or vice versa? It's a very decision-making process. So these are some of the results that we had from machine learning, where we used all this information that you can see on your screen and developed forecast for what the tool wear would be. And the plots over here, they show the confidence intervals on what is the cumulative tool wear. The contractor came up to us and said, hey, if we see anything above 30% or anything between 30% and 50%, we are just going to change the tool because we know it's going to wear out faster after that. So we ran those models. We gave them possible ring locations where their tool is going to probably wear out much faster or is going to wear out beyond 30%. So the black line you see is the median tool wear, and we estimated that the median tool wear would be just before 3200. But since this is a probabilistic assessment, we showed them a profile of where the tool is possibly going to wear out. And they came back with the intervention data, and surprisingly for us, because it was sort of a performance validation of the model, that the tool wear was observed to be within the confidence intervals of the model. So you can see the tool wear was approximately 40%. And the reason you can see the error bars over here is these are all visual. So there is obviously a 10% variability in what could be observed. A 40% to me could be 50% to someone else, or could be 30% to someone else. So we have added for that variability, and the red dot you see is the measured tool wear. So it falls within the confidence intervals, and that validates the performance of the model. Now, once we have the data for intervention 7, we stretch this arrow. We take from 0 to about 3100 all the data into consideration, and then we forecast for what's ahead. That's how the machine learning model is set up. So you can see over here, once we have the data at 31, almost 3140, we kind of take that into consideration and then start predicting from here all over again, using the same concept of using TBM data, ground conditions, and intervention data. So yeah, as you can see, domain knowledge, understanding what the ground is, understanding which TBM parameters is extremely important. Now coming to the last part of the presentation, and I don't know how I'm doing on time, but yeah, this is the last part where we talk about the settlement prediction. There is immense amount of work and research that's going on EPBM induced ground deformation, and they can be modeled with three-dimensional finite difference analysis, and you can do this using either Plaxis or FLAC or RS3 with decent accuracy. And that has been the focus of the industry so far, where you kind of model the liner segments, kind of model what the annulus pressure is going to be, what the grout pressure will be, what the face pressure will be, and then you can model the shield length. It's pretty complex. It requires expertise. It's a magnificent approach to model your ground conditions and TBM operation to get greenfield settlements. And this is something that we have already done. As a research group, we focus a lot on numerical modeling. So and you can see some of the measured surface settlement on the y-axis, and the settlement predicted by the FDA, which is the finite difference analysis using FLAC. It's a pretty great fit. When I say it's a pretty great fit, meaning what was measured in the field or what was predicted by the FDA analysis actually matched what was measured in the field, and it gave us confidence on, sure, these FDA models can be used for setting up the machine learning model, because the results from this FDA model are very similar to what is observed in the field data. And that is how this process has been applied. So what we're trying to do is replace the FDA modeling with an AI model. The whole objective is FDA models require a larger computational time. You can see the clock is almost colored. That means it's taking a larger amount of time. But if we use the variability in the ground conditions, the TBM phase pressure, the TBM grouting pressure, and do a 80-20 split, which is very typical in machine learning, which means you're using 80% of the data you have to train the thinking of the model, and 20% of the data you have to test the thinking of the model of how good the thinking has turned out to be. And that's what we're trying to do. We are trying to replace the FDA effort with an AI modeling effort. The big objective of this is predicting ahead of the TBM and predicting in real time. So let's say you're excavating ring number 1500, and then you want to know what would be your ground deformations at ring 1505. By the time TBM goes to 1505, you won't be able to finish running up a very computationally intensive FDA model. So for that, you would need something that runs fast, is based on how the TBM is being operated, and is also based on the ground conditions. And that's the motivation of bringing up an AI model. And these are some of the results from AI modeling on how they closely match the results from FDA modeling. And that is what I tried to show earlier. So the first step was obviously building confidence into the FDA model, and then building confidence into the AI model, making sure that your AI model can replicate the results from the FDA model. Again, very key is the domain knowledge. If you do not have the domain knowledge, you won't be able to proceed with appropriate preparation for setting up the AI model. So once we have done that, we kind of took into consideration, I want to show, we took into consideration about 16 input variables that had the soil layer depths, the geotechnical parameters that affected ground deformation, things like modulus, friction angle, effective cohesion, what TBM parameters, phase pressure, grouting pressure, of course, and then what was the cover depth, what were the groundwater conditions. So taking all that into consideration, we developed AI assessments on a certain section of the alignment to see how the model is performing. So on the next graphic over here, you see we also did a 95% confidence interval on maximum settlement. So the pink dots that you see are the measured settlement from extensometers and ground monitoring points. The black line within the plot is the median ground settlement that is expected given what the ground conditions were and how the TBM is going to operate. And this is where currently the TBM is. So as the TBM moves forward from 240 station onwards to up to 260, we are going to get more data and we are going to see more points, and hopefully they will fall within the confidence interval. So looking at something like this shows that there is sort of a confidence developed in how this model is performing. You can see the measured settlements are very close to the median. Also they are within the confidence interval bands. And we all are aware of what alert and alarm levels are on any tunnel project. So over here, now what we are trying to do next is understand what sort of phase pressure do you need to apply so that your ground deformations are less than your alert and alarm level. I mean, it's just going backwards, doing a back engineering or back analysis on TBM on tunnel excavation and tunnel induced ground deformation, and using these machine learning models to do that back analysis. So we are basically doing an optimization of what should be your phase pressure now if you want to bring this particular settlement at station 230 to 0. Right now, that settlement is about 0.25 inches. That's about an mm. But less than an mm actually. But yeah, what would you want to do to bring this to zero? So the whole objective of this is contractor's request where he says, I want zero settlements. Just give me a phase pressure that I should operate with, and just give me a grouting pressure that I should operate with. And these are some of the results, pretty basic, pretty new, but we are still working on this, trying to develop this. So on the top plot, you see the phase pressure comparison, which shows what is the phase pressure that is optimized that you need to operate with. And the blue is the phase pressure that is recommended from is recommended into the contract documents. You know, when a contractor starts on tunnel excavation, they prepare something called work plans. And in those work plans, they describe the geology and they describe what the phase pressure is going to be for the entire alignment. And that is the blue line that you're looking at. And the red one over here, the spikes, they are the actual operated TBM parameters, actual operated TBM phase pressure during excavation. So you can see a higher pressure is required to obviously cause zero settlements. You might come to me and say that's pretty obvious, but yeah, this is the phase pressure that would not cause any heaving. So we are taking care of that part as well, where we are not heaving the ground. And if you have a if you go to a higher confidence, say you go to a confidence of 95%, this value would pump up, and then there is the possibility that you can cause heaving of the ground. But right now, that's the approach that we are adapting, where we are identifying what the phase pressure is so that our ground has zero settlement, so that our TBM moves with maximum efficiency. And similarly for grout pressures over here, we look at grout pressures, what was recommended versus what was optimized from that machine learning algorithm, and how this is going to help the contractor in reducing the ground deformations. So that's one of the key aspects. Again, understanding the ground in the first place, understanding the groundwater conditions, and then looking at phase pressures. You need domain knowledge for this. You cannot hire a computer science graduate or undergraduate student to do this for you. You need to understand why you're doing, what variables you're selecting, and very importantly, how they are impacting your model, which are important variables, which are not so important variables, but you still need them. So that kind of overall assessment is required. And I guess with that, a few thoughts on AI application. So yeah, I mean, both toolware and settlement prediction, they are related to, they are very high risk. Obviously, the more higher quality data you have, the better will be your model. And the objective is to focus on Internet of Things. I mean, what you see, an Alexa or a Google Home, they're Internet of Things products, and you want sensors to be like that. You want to invest into or direct the sensors to show you the data in the first place, and then change the operation according what your model spits out as a result. So the long-term goal is to create an AI applicable to a variety of projects and conditions. As I said, you might argue that geology is changing and things are changing. My TBM has changed, my project has changed, but yeah, sure. I mean, the objective is to develop AI for all sort of situations. And it is absolutely important to capture the data that can be used for future AI modeling. So after doing 10 tunnels, if you're doing the 11th one, sure, use the AI model for the 11th one. But then when you're going to do the 12th one, you need to consider all of the past experience. So that's just my thoughts on AI applications. And before we wrap up, I just want to show something that I have been researching a little about, which is also called the tunnel information model. And I showed this at the start of the presentation. And I think AI is going to find a great opportunity of integration with tunnel information model. So you have different models from different elements of tunneling coming together, and then integrating with the AI stuff, and so that you can optimize your construction performance, mitigate tunneling risk, understand what sort of effort you're going to require, informed decision making. It's very key, extremely important. So yeah, the reason I say, because I see a very similar example in one of the papers that I was observing on tunnel information modeling, tunnel information model actually. So you see there's a tunnel project going on, pretty nice graphics if you ask me. And then they show the settlement data. In this case, the ground is getting heaved because of the way the TBM is operated. I think they had higher thrust forces over here. And again, if you had a machine learning model, you would get guidance on what should be the ideal TBM operating parameters at this location so that you don't cause it. And you can see the setting is an urban setting. So with what I was trying to come up earlier, I think it all stitches well together with this slide where you have time dependent visualizations, you have digital data, and then you have machine learning model all coming together and helping you understand how you should excavate, what sort of environment you are in and you should take care of. And as I said, with settlement, we can do what we applied earlier with those machine learning models. So there is a very high potential of AI getting integrated into the TAIym framework. TAIym is a little bit different from BIM, but yeah, TAIym is the word. And this is how eventually it's all going to look, understandably, that there is going to be a TAIym model, there is going to be elements of TAIym model. Then you have the combined CAD model or a BIM model, and you have finite element modeling. And there's everything coming together where either you're doing numerical simulations or you're doing AI. And that is how your project elements are going to get integrated in the end. And with that, yeah, I would like to thank TAIym for this wonderful opportunity to chat about AI and machine learning, and I hope this presentation was sort of helpful for you to look at. Thanks.
Thank you, Rajat, for this fantastic presentation and sharing what you have been doing uh, uh, in your thesis and bringing it to everybody.
Yeah.
So before I move on further, I would like to uh, ask people if they have any questions and they want to ask something from Rajat. So Rajat, we have one observation.
Yeah.
So I think the name is not very clear, but the person says, could you talk more about your probability and confidence levels in a very abstract sense? How are you approaching it? A lot of conditional probabilities, I guess.
Um, can the question be a little more elaborative to understand what are you trying to ask? Are you trying to ask how is it done, or are you trying to ask how to interpret what is being done? But yeah,
No,
if you, I'll answer both.
yeah,
Let's do
yeah,
that. I'll answer both.
yes, please, that'd be great. Yeah.
So yeah, whenever, okay, it's okay. How it was done? So okay, I'll come to that as well. But now I have warmed up for giving both the points. Um, so if you look at weather conditions in your city today, and if there is a chance of getting a rain, they would give you a result in the form of there is a 40% chance of rain today. So that is how probability is understood, right? Now, the point is when we are conveying results to someone, be it an engineer or be it a client or be it a contractor. You don't want to be ever in a situation where you are giving deterministic response. So if someone asks you, how many boulders do you expect within this tunnel project? If you come up with an answer of 100, and if more than 100 boulders are encountered, then you're going to get claims from the contractor. Similarly, if there are less than 100, then you have not evaluated the ground conditions and have invested into the project a whole lot more than you should have. So you're at loss at both the ends. But what if you tell someone, hey, there is a 60% probability that you're going to encounter 100 boulders? So this gives a more quantitative assessment. And that's why I love talking about and relaying my results in terms of probabilities and confidence intervals. And how was it done? It is math. It's just that if you have sufficient data, let's say you have numbers 1 to 100. So now you have 100 rows in an Excel sheet going from 1 to 100. All you need to do is understand what numbers fall in 5% confidence and what numbers fall in 95% confidence. So it's just understanding and applying the logic of statistics and math, where you identify what your confidence intervals are. And confidence intervals actually give an indication of how confident you are, right? So if I'm telling someone that I'm 50% confident, so you can imagine how confident I am. But if I'm telling you if I'm 95% confident, so it's pretty easy for someone to understand. Yeah.
Yeah, Rajat. I think what I understood as a crux is that there will always be uncertainties.
Right.
It's not a clear science, and interestingly we have been doing it through our careers. Artificial intelligence is a new concept where computers and algorithms are there.
Yeah.
But if you ask somebody who is sitting on TBM and working there, he
Yeah.
would exactly tell you when to replace the tools. He
Exactly.
knows,
Yeah. Yeah.
he feels the ground. There are some natural, I would say, it's not artificial intelligence. I would say it's natural intelligence. He's processing
Actually,
that
it is.
information. That guy is actually looking at the data, the torque that you have on the cut ahead, the
Yeah.
speeds that you are going with, and what type of ground is ahead. And he already has those algorithms inbuilt into the mind to predict it, and
Right.
with a fair certainty as well.
Right.
It's just a way of bringing new technologies into it, and to bring a more uniformity and a structure into it.
Yeah.
Uh,
Yeah.
because at the end, otherwise we are relying on the experience and the skill set of an individual to take that decision.
Absolutely.
But
Absolutely.
when we have computers and mechanics into it, then we have a system which can predict uh, the outcomes with more certainty. And
Yep.
with time, when we have more data and it's processed, it becomes better with time. Uh,
Yeah.
so imagine 10 TBM operators sitting in the same room after 10 years and predicting it with much better accuracy. So
Right.
that's how the data plays. So if we have information from 10 different projects, then we have much more accuracy into prediction.
Yeah.
So
Yeah.
definitely there are many factors which come into play. Definitely there are many variables, uh, and it cannot be certainly said that what's going to happen into the ground. But there is a possibility that we can make our decision making more efficient by utilizing the previous experience and data.
Yep. Yep.
So
That's what.
I think that gives an answer to this question, I guess. And we have one more person, Harsha, who's asking about. I can see the whole message. Oh yeah, Harsha says thanks for more detailed application of AI in TBM.
Mhm.
As you said, calibration is very important. For suppose in case of deformations, we are calibrating the results with numerical analysis results. But at first, as a design engineer, we need to calibrate the constitutive behavior of the models considered in the numerical model.
Right.
So how have you come up with the models to be considered and also made them to produce results to contractor?
That's an excellent question. That was one of the biggest roadblocks that we had when we started with this project of how are we going to come up with an acceptable constitutive model, and then how are we going to run this in time to apply and to provide this to contractor. So how are we going to run this in time is working 24 hours. That's the answer for that. The easy part, you sit 24 hours, do it, keep on doing it, have multiple machines, have a bigger computational capacity, and just keep running models like anything. And constitutive behavior of the model, that comes with experience. If you have done enough models in the past, you would look at the type of geology, type of geotechnical parameters and conditions and lab results, and you'll be like, maybe I would just use this particular constitutive model and that will be all. Understanding that's why I said domain knowledge is important. Drained and undrained conditions, you would want to know by the time you select your constitutive model and what sort of conditions are going to exist, what sort of ground conditions I am in. And that's how we were able to do it fast, because the people who are doing it are in the final year of their PhDs. So if they don't do it now, they won't be doing it ever. So I guess it was high time that we did things fast because we understood them. And but yeah, we needed a huge amount of computational effort to do it.
Great. I think that's all the questions that we have from the audience.
Yeah.
I'll just go ahead with few more announcements before I close this, and thank Rajat for today. I hope my screen is visible.
Yeah.
Okay. So we have our biggest annual event coming up in 2021 in November. We are going to have our first annual conference. The theme of the conference will be Underground Space Challenges and Opportunities Ahead. It will happen alongside with Tunnel Asia Conference. Most probably it is going to be in Mumbai if it happens in person, or it would be online if we continue to have restrictions due to COVID. And we'll be sharing the information on the last date to submit the abstract for the conference very soon. So keep an eye on the emails from TAIym. Then there is another big news. We have SITA 2021 Symposium of Young Tunnelers of Asia. We held Malaysia last year to do the first one, and we co-founded it. And this year India is hosting it on 7th of August 2021. The preparations are already ongoing, and by the end of January we will have the complete schedule when the papers can be submitted and when they will be presented. We are in touch with many countries, and Japan, South Korea, Malaysia, Hong Kong, New Zealand, and UK have already confirmed their participation. With Singapore and Australia, we are awaiting, and we are hopeful they will be confirming within a week. So two big things coming up for TAIym, and of course with many more webinars where people will be sharing their experiences such as today. We have our new blog, which is live on TAIym blog. So you can check your email. The links have been shared. And it's a very interesting story of a week where Mr. Ahmed visited Banial and USVRL project, where he took amazing photographs. Well, every photograph is amazing if it's from Jammu and Kashmir, and a very ambitious project. where we have lots of bridges, lots of tunnels, and he summarizes his journey in this blog. It's very interesting. I would really recommend to have a look and go through it. So that's it. That's it for today's webinar. Thank you, Rajat. Thank you for being here and interacting with people from TAIym. We will be uploading this recording on our YouTube channel, and I'm sure there will be many more views, and our young professionals and students will learn from these experiences. Thank you very much,
Yeah,
Rajat. Thank you for
thanks
being
so
here.
much. Yeah, thanks for having me.
Thank you. Take care. Bye.